Hello, everyone. My name is Alexey. I'm a committer and PMC member of the Apache Ignite project. And today I would like to talk about the Ignite native persistence feature, which was added a couple of years ago. And this would be sort of a retrospective talk, and we'll cover the high-level architecture of the native persistence, and we'll not cover and take a look into the protocols. So we'll only look into the persistent storage itself. And we will also see some trade-offs and implementation choices that we had to make, and some obstacles that we faced when implementing this feature in Java. So let's start with the goals and why we needed to add persistence to Apache Ignite in the first place. Probably someone may remember, but in Apache Ignite 1.x, there was a feature that was named file store, persistent file store. And this feature sort of provided the ability to store durable data on disk in Apache Ignite cluster. But it had several downsides. The first downside was that if you restart your cluster, in order to start serving SQL queries, you need to preload all the data that you previously loaded into the cluster. And the more data you have, the more time it takes to preload the data. And for example, if you had hundreds of gigabytes of data per node, the cluster warm-up would easily take hours, from 2 to 3 hours, for example. And obviously, it's not very convenient for maintenance. The other restriction that the old file store had is that the keys index was still residing in memory. So, for example, if you can offload your data to disk, but the amount of data that you can keep in the cluster was still limited by the amount of memory, even though it was much simpler to store more data because only keys were stored. And over time, these restrictions were more and more inconvenient for Ignite users. So we decided to take a step further and introduce the feature that would allow two things, at least. First is to serve, to have fast restarts and allow to serve SQL queries as fast as possible after the restart. And in this architecture, you would not need to preload all the data. And for example, if a query is sent to a cluster, you would only preload the data that is required to answer this particular query. And we also wanted to remove the second restriction and to have an ability to keep significantly larger amounts of data that there is RAM available in your cluster. And another sort of a technical restriction, we wanted to have the same architecture for in-memory and persistence layer storage. And the reason behind that was keeping the code simpler, because otherwise we would have two different implementations of the storage engine, and this would complicate the code maintenance. So after initial research, we decided to employ ARIES architecture. It's a well-known approach in databases, and it provides basically it provides all the necessary requirements that we had at that moment. It supports arbitrary data structures. In other words, we were able to implement the data storage itself, the SQL indexes, and all auxiliary data structures required for internal bookkeeping. Obviously, it supports the architecture. The ARIES architecture supports recoverable durability, which allows us to store data on disk. And it also supports transactions, because transactions were in Ignite from the early stages that I can remember. So let's first take a look into what this ARIES approach is, what are the parts of this approach, and how it works underneath in general. So first thing that we need to know is that the data that all the potential data that we want to store on disk is split into blocks of equal size, and these blocks are called pages. Each page has a unique identifier. The ARIES paper doesn't specify how this identifier should look like. It just requires that given an identifier, we should be able to locate this particular page on disk. There are multiple ways of implementing this, and one of the examples is given in the slides. So for example, we can split the logical identifier into two parts. The first part would be the file ID, and the file ID would be, for example, encoded in the file name. And the second part is the page index. And given that the pages are of equal size, given the page index, we can immediately calculate the offset of this page in file. There are more complex approaches, for example, to have a relocation table in each file, which translates logical IDs to physical offsets. But again, this is not something that should be particularly implemented according to the architecture. The second thing that we need to have in order to have a durable storage is the ability to load these pages into memory. And to accommodate for this ability, we allocate a chunk of memory which holds the data that is loaded from the disk. And essentially, we also split this large chunk of memory into pieces, and each piece represents a page buffer. So a page buffer is essentially an image of a page that is loaded into memory. Each page is protected by a ReadWrite Log, and Ignite is a multi-threaded system, and in order to accommodate and provide necessary synchronization primitives, each page has a read-write log. So this means that single page is the minimal granule of the data that can be read or write atomically. So you cannot read from a page and not log this page. And this log is a read-write log, so readers acquire a shared log and writers acquire an exclusive log. Now, if we remember our initial goals, we can remember that we want to store more data than there is memory available on each node. This means that the amount of memory and the number of page buffers that are available for Ignite process is smaller than the number of pages that is stored on disk. This means that we need to have some sort of indirection, and to know which page buffer holds each particular page. And this mapping is implemented as a translation table, essentially a hash map, which holds and maps logical page ID to the address of a page buffer, which holds this particular page at this moment. There are situations when let's say we have preloaded, like in this picture, first 4 pages and they're sitting in the memory, and some query is trying to access page with index 5. If we go to the relocation table, we see that there is no page with such ID loaded into memory. And at this point kicks in the process which is called page replacement. What it does, it selects some page that is needed to be replaced. Again, the algorithm which chooses this page is outside of the scope. But usually it's the page that was accessed less frequently, or which was accessed the longest time ago. Now that this page is evicted, the page buffer is free, and we can load the page with index 5 to the memory. It's well, and essentially this is how page replacement works. We can see that when there is a page miss in the page memory, we read the page from disk, and this essentially limits the throughput of the system, because, for example, if your disk has that many number of IOPS, is capable of performing that many number of IOPS, and, for example, each cache get performs 10 page reads, then in worst case scenario, you are limited by the number, your throughput of reads per second is limited by the number of IOPS divided by 10. So that's why it's very important to have more memory available on the nodes. And essentially, this was the primary use case that Ignite was targeting, because originally Ignite was an in-memory data grid, and we still wanted to maintain this status, but just wanted fast restarts. So now that we have a foundation for the ARIES architecture, we have pages, we have page buffers, and we have mechanics that allows us to access arbitrary page, we may start to build data structures. And in order to make a data structure persistent, it also needs to be page organized. For example, we can build a durable tree, we can build a durable free list, and all these data structures are present in Ignite, and they are page organized. In order to save links, in order to link pages between each other, we are still using the same logical page IDs that are used in the indirection tables. And finally, one of the most important pieces of the ARIES architecture is RightHeadlock. And it's important because it provides the ability to perform crash recovery. Essentially, the RightHeadlock is a append-only file or a set of files which holds the information of the changes that were applied to the system. Logically, semantically, data that is written to RightHeadlock can be split into two categories: logical records and physical records. Logical records represent information in terms of operations that we apply to the key value store. For example, if we do put, the put operation, the logical records for the put operation will contain the key and the value that was written to the key value store. On the contrary, physical records are not tied to the operational semantic, but they rather describe the physical changes that are applied to pages. For example, if we change bytes from 10 to 50 in a certain page, the physical record will contain this information. And RightHeadlock essentially is a single point of truth, and if a process crashes, the information is read from the RightHeadlock and reapplied to the persistent storage. And ultimately, we could have used, theoretically, we could have used only the RightHeadlock, but this would require an infinitely large disk. And of course, this is not practical. And in order to be able to truncate the write-ahead log, there is a mechanics that is called checkpointing. And what checkpoint does, it basically collects all the changes that were applied to the memory and write these changes to disk. So let's now see how the coordination between updates and checkpointing is implemented in ARIES with Ignite specifics. So the first thing that we need to know is that in order to coordinate checkpointing and updates, there is a read-write log called checkpointing log. And when an update arrives to the storage, the first thing that happens is that this update acquires a shared log. So this means that multiple updates can be concurrently applied to the storage at the same time because the log is shared. Once the log is acquired, a logical record is written to the write-head log. If write-head log is synced to the disk at this point, we actually can be sure that the operation is persisted. So in the case of a process crash, this update can already be replayed and applied to the storage. After the logical record is written to the write-ahead log, update proceeds and updates all the necessary data structures. So for example, it inserts data into the data pages, it updates the primary index tree, it updates secondary SQL indexes, if any, it updates free lists if we change the layout of data pages. And part of this, as a part of this protocol, when the changes are applied to pages, physical records are written as well to the write-ahead log. And one of the important things in this protocol is that physical changes to the write-ahead log must be written before the write log to the page is released. So essentially, the protocol is take a page, acquire write log, put physical record to the write-ahead log, then release the log. So once all the data structures are updated, the shared log is released. And we end up, in this case, we end up in a situation when there is a number of pages that are kept in memory, which content differs from the pages that are currently written to disk. Such pages are called dirty. And the essence of a checkpoint is to write these pages to disk in order to be able to get rid of the portion of val of the write-ahead log, which was responsible for these pages. So let's now take a look at the checkpoint protocol. The first step in checkpointing protocol is exclusive log acquisition. Once the exclusive log is acquired, we know that there are no in-flight updates to the pages. And at this point, all the pages are mutually consistent. So this is the state that we want to transfer to disk. When the log is acquired, we do a sort of a lazy copy of all the pages that need to be written to disk. In fact, we do not copy the actual data from these pages, but we copy only the logical identifiers of the pages that need to be written to disk. And obviously, we do this to minimize the amount of time the exclusive log is held. Once the page identifiers are copied, we release the exclusive log and the further updates can proceed. In the case when the next update wants to write to a page that is supposed to go to disk, a copy on write happens and the original state of this page is sent to a temporary buffer that is called checkpoint buffer. And now that the checkpoint log is released, we can transfer the pages to disk. essentially, from the bird's eye point of view, this is the all protocol of the ARIES architecture. Of course, for the sake of this talk, for simplicity, I omitted several points, but it should be sufficient to discuss the implementation details that I have in mind and wanted to share with you. So first thing that we faced when we started implementing architecture was a question how to actually what should be this read-write log that is protecting each page. The first and straightforward solution is to have a separate instance of JavaUtil concurrent random log for each of the pages. But we were targeting hundreds of gigabytes of RAM, and given that each page takes from 4 kilobytes to 16 kilobytes of data, it would mean that we would end up with hundreds of million pages in memory. And if we have a separate log for each of the pages as a Java object, we would end up, first of all, with a large amount of objects on heap, and this would create waste of memory, and it would not help with garbage collection, because one of the points, like a secondary point, but still of moving to page memory, was moving to off heap. And if we would keep hundreds of million Java objects in heap, this would be the same problem. An alternative approach to keeping the logs and protecting pages would be to create and destroy log on demand. So for example, if you want to access a page number 10, you first make sure that you create a log for this page, then you acquire this log, you do the business with the page, you release the log, and you destroy the log if it's not used by anyone. But this approach requires an additional synchronization points in order to coordinate log existence, because we don't want that multiple threads end up with different instances of the log for the same page. So we needed some sort of coordination for this case. And since on each update multiple pages are acquired, multiple pages are written and read, we would allocate very large amounts of Java objects. On top of that, keeping logs separate from pages implies bad processor cache locality. So what we decided to do is to inline the log itself in the page buffer. And of course, this is not a full-fledged reentrant log, but still it provides all the necessary infrastructure to implement the ARIES architecture. The log itself consists of 4 fields, 3 of which are quite generic and common for the logs. They hold the number of currently waiting readers, the number of currently waiting writers, and the log state itself. It can be in shared acquired state or in exclusive acquired state. The final field, which is called tag, is used by Ignite to help us prevent and detect ABA problem. And ABA problem is when you want to access a page with a certain page ID, but due to concurrent processes, the page ID is not of the same type that you expect it to be. And this often happens, for example, when you run a SQL query and you have a cursor on a large index. So in this case, if you are positioned on a certain point in the index and the index is changed, you may end up reading a page with the same ID, but semantically of different data. And this tag is something that is embedded into the log and helps us to avoid this problem. From the implementation standpoint, the lock is not fair, and theoretically there are situations when reader or writer threads may starve. We try to give preference to writer threads, but also employ some randomization that helps us to balance between readers and writers. And the second point from the implementation standpoint is that the lock is not reentrant. But actually, since the native persistence was implemented, there was not a single time when we wanted or regretted that this log is not reentrant. And so the log itself is only 8 bytes, and it's very lightweight, and it provides all the necessary infrastructure for page access synchronization. Um, so second implementation choice that probably the most visible to the users is the notion of the sharp checkpoint. So from the checkpointing protocol, we saw that we acquire a exclusive log for in order to capture the state that needs to be written to disk. And since this state is fully consistent, the checkpoint is called sharp. An alternative approach is called fuzzy checkpoint, but this approach is much harder from the implementation standpoint, and it also limits the number of data structures that can be implemented, because when you switch to sharp checkpoint, the data structure itself needs to be written in such a way that it is recoverable. When the sharp checkpoint is used, the data structure can be of arbitrary complexity, and it still can be fairly easy checkpointed. The downside of this approach is that the lock is exclusive, and even though we try to hold the exclusive lock only for milliseconds or sub-milliseconds, it still affects the high percentiles for the latency. And the checkpoint buffer and checkpoint related configuration properties are the parameters that are most often tuned when you work with persistence. The next thing that again users face, sometimes they face it, is the concept of file per. The choice here was whether to keep data of each partition in a separate file, or write all the data that is related to this particular node in a single file, or to a set of files that is not direct one-to-one mapping to the partition numbers. And the choice here was given to the file per partition approach for a number of reasons. First of all, it allows us to have a transparent mapping from pages to from logical pages this to uh, to pages in files, to pages of sets, and it simplifies several internal processes inside Ignite, namely related to rebalance and to taking snapshots. Because when you take a snapshot, one of the modes that is beneficial is to have a single copy of partition in this snapshot. And if data was mixed inside this partition file, it would be very hard to deduplicate this data in a distributed fashion. The downside of this approach is that if you have secondary indexes, it's not very easy to drop a particular partition, because for example, if we have a shared index for two partitions and we were to drop the second partition, we would end up with a broken index. So that's why before actually dropping the partition file, Ignite has to clear the data records one by one, and only then release the file. Another thing that is related to the ARIES implementation specifics is that tree scans, the data scans are always index organized. And this means that when you scan a large number of data, you may end up reading the same pages over and over again. And of course, this would be an important optimization to avoid this duplicate page accesses. But originally, Ignite was optimized and was targeting OLTP use cases, and for OLTP use cases, these scans are not often. However, the index access works for small result sets very well. And finally, an interesting part of the implementation is relocation table, which holds and translates the page IDs to page buffers, as we saw it before. And one of the important operations for this table is again partition eviction. And if you were, for example, evict a partition from a simple hash table, we would need to scan the whole partition, which again may be a time long operation. In Ignite, we introduced a concept of generation for partitions and stored this generation with the partition with the page identifier in this table. And for example, when we evict a certain partition, we simply increment the generation number. And once we've incremented the generation number, the corresponding entries in the hash table are considered to be invalid and virtually free. So this allows us to have a big O1 clear operation for any partition. So let's recap what we saw from the architecture point of view and from the implementation details. So first of all, you need to remember that if you have more data than you have available RAM, you would eventually hit disk when you read data. And thus, the more data feeds in RAM, the better the performance you have. If you are working with a use case where not all the data fits in RAM, you would want to have a disk which sustains a large number of IOPS, because in most cases, Ignite is designed to provide best performance for point accesses, and this implies random accesses. And if you have arbitrary workloads, you should still try to transform them and optimize in order to make them look or work more like OLTP. So you need to avoid full scans and try to employ per partition scans. Ignite has specific API that can efficiently preload the partition into memory. And of course, use data collocation and read data by particular key, and use small data sets, small result sets. As for the potential improvements that can be implemented or already planned for Ignite, of course, there is a stream of development that aims to support hybrid transactional and analytical processing, which will not suffer from this random accesses and will read data very efficiently. Another stream that can be implemented is to use or implement right optimized engine, which will avoid reading data from disk when you do appends or blind writes and you don't need previous values. And here, sort of, there are two directions. The first one is incremental checkpoints, which are, as far as I remember, are currently in the design stage, and you can take a look at the corresponding EAPs in Ignite enhancement proposals. And another approach, which is also widely used and famous, is log-structured merge tree. And finally, quite local improvement, but still very important, would be to support page level scans, and probably some or all of these improvements will be implemented in Apache Ignite 3.0 or 3.x. Apache Ignite is a very under very active development, and currently it transfers to the next stage, which is Ignite 3.0. So I would love to see more contributions, and if you have any ideas or were shy to come to Ignite community, don't be shy, and you can always reach out to developers or users list, or if you have any questions, you can reach me out directly. So I think this is all from my side, and we can now I cannot try to answer any questions.
Great. Thank you very much, Alexey. If I remember correctly, you were going to give a talk very much like this in London, like nearly 18 months ago, I think. I ended up giving a similar one, but yours was much more thorough. Your understanding on this is definitely way beyond mine. So thank you for that. I don't see any questions coming in. We probably have another minute if someone wants to kind of quickly dash a question in. Otherwise, yeah, obviously really appreciate your talk. Kind of huge amounts of depth in there. I learned a lot, certainly. Yeah, if there's no questions immediately, Alexey might be going into the hall afterwards, which is a link on your left where you can kind of join people, ask kind of questions of the speakers. If you are looking for more general advice on Apache Ignite rather than details of this course, you can also go to the booth where we have a couple of Apache Ignite experts available. Thank you once again to Alexey.
Thank you, everybody.